Hi, my name is Jakub Svoboda, and I will tell you something about a paper called Simplified Game of Life, Algorithm and Complexity. I suppose that all of you are familiar with the game of life, but to be on the same page, I just briefly define it. We have a square grid, as here, and some squares are yellow and some are gray. We say that a yellow square is alive and gray is dead. Live square needs some living neighbors to cooperate, but if it has too many of them, they compete. The game of life simulates that. The grid refreshes in steps, and a dead square that has exactly 3 live neighbors becomes alive, otherwise it stays dead. Live square that has 2 or 3 live neighbors stays alive, otherwise it dies. Here we see a simple simulation and all live squares died out. But even from a simple position, the game of life can be very complicated. Here you can see such an explosion. The game of life is interesting because the rules are simple yet rich enough to simulate a Turing machine. Here we have a table of the number of neighbors and their changes. We see that live vertex needs 2 or 3 living neighbors to survive, and dead needs exactly 3 to become alive. We can look at this the other way. Live vertex can die either from having too little live neighbors or from having too many of them. In the paper, we simplify rules for game of life in 2 ways. First, live vertices can die only from underpopulation. The second live vertices can die only from overpopulation. So one dynamic uh, has only that here and other cells are alive, and other one has only that here and others are alive. So here we have the tables, and every rule is characterized by 2 numbers, k and l. In both dynamics, that vertex that has more than l neighbors becomes alive. Here, in underpopulation, if live vertex has less than k living neighbors, it dies. In overpopulation, if live vertex has more than k living neighbors, it dies. We can see it here, and note that only difference between underpopulation and overpopulation is this inequality here. Our dynamic happens on a general graph. We show that the underpopulation rule has only simple behavior, but surprisingly, the overpopulation is complex as a game of life. Let's look at examples and the underpopulation first. There is a friendship graph here. Everyone either wears a mask or not. You are here, and if a lot of friends wear a mask, you start wearing it. The fact that you are wearing a mask can even convince some of your friends to wear a mask too. Here. Now let's look at the overpopulation. Instead of wearing a mask, we look at the fashion. You and your friend are fashionable. You wear a red shirt, others wear plain black. After your mutual friend sees you, he decides to try it too. But now you see too many of your friends with a red shirt. It's a mainstream, so you revert to the black one as your friends do. But some people might start wearing reds, such as here and here. From our examples, it is clear why we would be interested in solving such problems. Everyone wants to influence network. The question might be, who should wear a mask or fashionable clothes first to spread it to as many people as possible. To describe the hardness of this problem, we define a problem called reach. Does a process get from a position A to a position B? We know that it is hard to compute this problem for a game of life. There is another interesting question. What makes a model computationally hard? There is a scale between the rules, how complicated they are. At the first, the trivial, for instance, everyone dies in the first round, which is easy to compute, and game of life, which is hard. On this scale lies a set of rules that is the simplest hard and the most complicated easy. Here and here. This could help us to understand what is the necessary condition for hardness. We show that the underpopulation is on the side of easy problems and the overpopulation is on the side of hard problems. Even though they are almost the same, they differ only by one inequality. In our paper, we showed that the underpopulation rule gives a rise to a dynamic that is not very complicated. Given any graph and starting position, the behavior is simple. First, some steps are unpredictable. We can just simulate them. But then the process settles and oscillates between at most two different states. The number of these unpredictable steps is polynomial, so we can enumerate the reachable states in polynomial time. The basic idea of the proof is that the current state of vertex V influences the state of V two steps in the future. If V is alive, as here, the next step, its neighbors are more likely to be alive. Thus the next step, V is alive. If V is dead, next steps, its neighbors are dead, and V is dead the next one. In the paper, we formalize that idea and prove it. Before the oscillation happens, there might be some irregularities, but this will settle in the number of steps linearly proportional to the size of the graph. Now, I describe how to create a Turing machine using overpopulation rule. For any polynomially bounded Turing machine and its input, I describe a graph and a starting position such that completely dead graph is reachable if and only if the Turing machine accepts given input. Our construction is for k equals 2 and L equals 1. That means a new vertex becomes alive if it has at least two neighbors and dies if it has two or more neighbors. But we can slightly change the graph to get different values for k and L. First, I describe basic components, vars, logical gates, and memory. Then I say how to combine them to create a function and blobs. Finally, I show how to simulate a Turing machine using these gadgets. You can imagine the construction as a white or dead graph where there runs black or live signal, and maybe some black vertices that store data. First, there is a wire. We use it to transport a signal between more complicated gadgets and pad shorter gadgets. On the left, we have 4 vertices, and the previous gadget is responsible for erasing them after 1 round. Similarly, as we are responsible for erasing our output. Next round, there are these 2 vertices, black and others, white. The signal cannot go back, just forward. Because back, everyone has only one living neighbor, but to the right, there are 2 living neighbors. Next round, these 2 vertices make these 4 alive. Again, signal cannot go back, but now we see that everyone dies because everyone has at least 2 neighbors. But these will become alive. And this continues on and on. Using the same ideas, we create splitter. It creates a new signal. We can see it here. By combining signals, we can create logical gates, AND, OR, and NOT. 2 signals come to the gadget, and the result goes out. AND and OR are pretty straightforward. For AND, we have 2 inputs, and you see that signal goes through only if both of them are true. Or the same, but even if one is true, it's enough. But NOT gate needs a clock signal. Here it is. Because we cannot generate a live vertex from dead ones. So we see that signal goes through if there is no signal on the bottom one, but it's completely erased if there is. What else is crucial is a storage unit. It has 2 inputs. One input changes the inner state. The inner state can have 2 states. And one input is used to recover the state without changing it. It works like this. Here we can send a signal and it stops here. And these vertices are alive. Sending a signal again by this input, we can erase the signal. If there is no stored signal and another one goes through the input too, nothing happens here. But if there is a signal, it creates a new signal that corresponds to the value of the storage unit. And note that it doesn't change the stored signal. Now we have everything to create a function. Imagine that there are n signals going from the left. One of them is true. We can interpret it as a binary number. Then we can use our logical gates to compute any function and this input and on this input, and it uses only 2 to the n logical gates. With functions, we can create a blob. Blob's input is a signal that corresponds to a state of the Turing machine. The blob has some storage units that store the symbol of the tape. When a signal comes to the blob, we recover the content of storage unit and then send both signals to a function that computes a new state of the Turing machine and a symmetric difference between the current symbol and the new symbol, and where the signal should move. So we have a function that has two inputs. One corresponds to a state of the Turing machine, one to the cell memory. We compute a function how we should change a memory to have there a new value, and then we send a signal either to the right or to the left, depending whether the head of the simulated Turing machine should go to the right or to the left. If we connect more blobs and we initialize them with the state, and we initialize also position of the head, of the Turing machine head, and note that we cannot just put the Turing machine head there. We have to start the simulation, and signal goes to the blob, and the transition function is computed. From that, memory is updated, and the state is changed, and the head is moved. This happens on and on until the end state is reached. And this is exactly a Turing machine. So just to conclude, I described two very similar processes, but one of the processes is easy to compute and the other process is as expressible as the Turing machine. Thank you for your attention.